So this is the next question that we have. This is exercise 1.4.2. So let us see this question. This question says that suppose V1 N1 and V2 N2 are two subspaces such that any element of V1 N1 is orthogonal to any element of V2 N2, then what are we supposed to do? Show that the dimensionality of V1 N1 ring sum V2 N2 is N1 plus N2. So this is the question that we have, and we need to prove this question. So before we prove this question, we need to see certain definitions and certain notations that is being used in this question. So first of all, this notation of Vi Ni means that this is a subspace this is the ith subspace, this is the ith subspace of the vector space V, and this has a dimensionality, the subspace has a dimensionality of Ni. So Vi Ni is the ith subspace having the dimensionality Ni. Also, we need to see what this kind of a sum notation means. So this kind of a sum notation means that, let us say, so we are basically right now defining this special kind of sum of vector space. So let us say we have two subspaces so given this, we define their sum denoted as VINI ring sum Vj and j. This sum is, by the way, this will be some another subspace Vk having dimensionality Nk. So we define this sum as the set containing 1 all elements of Vi and I. Next, it should contain all elements of Vj and J, and it should contain all linear combinations of the above. So this sum of vector subspaces is defined as a vector space, a subspace containing all elements present in both of these subspaces, as well as all the linear combinations of all the vectors present in both these subspaces. So this third statement is essentially present to satisfy closure property, because for closure property we need that the sum of two elements should also be an element of that vector space. So this is the definition of the sum of two subspaces. Now we can proceed to solve this question. So we will see. So by definition, we see that V1 N1 has dimensionality N1. So if it has dimensionality N1, then that means it will have N1 mutually orthogonal vectors as the basis vectors. So if this is by the definition of dimensionality. So this means that there will be N1 linearly independent basis vectors this linearly independent basis vectors can be made orthonormal by Gram-Schmidt. By now we all would be pretty much familiar by Gram-Schmidt. Similarly, V2 N2 has dimensionality N2, so it will have N2 linearly independent basis vectors. Again, these can be made orthonormal by Gram-Schmidt. Orthonormalization. So now if we take all the N1 independent vectors from V1, N1 and all the N2 linearly independent vectors from V2, N2, then we will get a vector space containing all vectors of V1, N1 and all vectors of V2, N2 and also their linear combination. So let me write down the statement. Taking all the N1 and n2 linearly independent orthonormal basis vectors will give us, this will basically span, so it will give us a vector space containing all vectors of v1 n1 and all vectors of v2 n2 as well as all linear combinations. So these n1 and n2 vectors will span the space of the sum of these subspaces. So thus these n1 and n2 linearly independent orthonormal basis vectors will span the space v1 n1 ring sum v2 n2. Thus we can see that since we have n1 and n2, n1 plus n2 linearly independent orthonormal basis vectors in the space v1 n1 plus v2 n2, therefore v1 n1 bring some v2 n2 has dimensionality of n1 plus n2. Since it has n1 plus n2 linearly independent orthonormal basis vectors, linearly independent orthonormal basis vectors. So we have proved this question. In this question we were supposed to show, we were supposed to consider two subspaces and then we were supposed to form the sum of these two subspaces and show that the dimensionality is given by n1 plus n2. Note that the condition given over here was that any element of v1 n1 was supposed to be orthogonal to any element of v2 n2. Where have we used this property? We have used it here when we are considering the combination of n1 and n2. So n1 is linearly independent basis vectors and n2 is linearly independent basis vectors, but taking n1 and n2 together also forms linearly independent orthonormal set. Why? Because each of these n1 is orthogonal to each of the n2. So let me write that down explicitly. So why we are able to get this n1 plus n2 is because each of the n1 basis vectors are orthogonal to each of the n2 basis vectors. That means none of this n1 would be parallel to any of this n2. So, any basis vectors from n1 of v1 n1 is not going to be parallel to any basis vector from the n2 basis vectors of v2 n2. So the orthogonality of each of these elements is being used when we make the statement of collecting n1 basis vectors from the first vector space and n2 vector space, n2 basis vectors from the second vector space, and adding them up together, combining them to get the dimensionality of n1 plus n2. So this is a very important point which is necessary. Otherwise, if we have some vector from this n1 parallel to some vector from this n2, then we will have to consider them as only one vector. It will not be one from this n1, one from this n2, adding them up to give us n1 plus n2. Otherwise, let us say if one of them is parallel to the other, then it will be less than n1 plus n2. We will have less number of basis vectors in the vector sum so then the dimensionality will be less than n1 plus n2. So the orthogonality is very much essential. This orthogonality ensures that we get the dimensionality of n1 plus n2.